Okay, I'm going to look at sections 4.5 and 4.6, and we're going to look for a moment of a force about a specified axis, basically continuation from 4.4. Okay, so here's an example. You're using this wrench or tire wrench, lug nut wrench to take off a tire, and you provide a force acting at a certain distance from from the point of the nut itself. What you're really concerned with, though, in this case is the actual rotation or the moment about the axis. In this case, would be y, right? It's not really if your concern is about a point. You're more concerned about it. What is the torque, or what is the moment about an axis or a line of action? Okay, and in this case, the line of action would be along y, right? And the real point of this is that what amount of this torque is used to actually either tighten or loosen this bolt or this nut. Okay, so you can actually come up with this if you think about it like in two dimensions, where you have like the x and y is a plane. You can actually break this up and determine what the actual moment is about that axis. And really is, if you think about it, it's going to be whatever this distance is times this force. Assuming this force is vertical, right? So this is right along the parallel to the z-axis. Okay. So in this case, what you're doing is you're just finding essentially, here's the angle. You're finding this side, right? The length of this side, which is essentially the length of this. Okay. So you can do it like this. Okay. This is one approach, right? If you have it in two dimensions, this is one approach to find it about an axis. Okay. And a more general approach, what you can do is you can do two parts to this. The first part is finding the moment about a point, some point. In this case, we're looking for the moment about A. Okay, this is A. This is the line of action of A. It could be an axis, but this is just some line of action A. And what we want to do is we want to find out how much of the torque, the initial torque we have, is used to turn, about this line of action. Okay, about A. How much of the moment is about A? All right, which would cause rotation about A. So it could be that maybe this is a bolt down here, and you're trying to figure out how much is to use to either tighten that bolt or loosen it, as an example. Because there's two basic steps to this process. First thing is you want to find, in this case they show you about point O, but you need to find the moment about some point along this line. Okay. And in this case, the origin is about a line, and you're given information related to the torque that's about that line. Okay. So what we could do is, we have some force. Oh, so here's the force acting at some distance. Okay. Here would be our F. And our R is basically the vector that represents from O to that point A. Okay. So the first part is you find that. You find the moment R cross F. Okay. Now from that, if you remember from previously when we talked about dot product is like the projection of a vector on a certain axis, okay, or a certain line, or a line of action. So this is a vector, and if we wanted to find out how much of it is along this line, we just do the dot product u of a, which is just the direction vector that represents this line of action A, dotted with our original, our moment about some point on this line. In this case, like we said, we know O, so we know it about the moment about the origin. You dot those two together, and what happens is the end result is projection of this moment, MO, that we found originally about this axis. How much of it is projected along this axis. Okay? And you could do this in general, right, for any vector. Okay? Well, we could do that as a two-step process, right? We could do the cross product by itself, and then we can do the dot product. Or we could just do the triple scalar product. And the way we would do that is you just put in, instead of, I, j, and k here, and find the determinant, you just do UAX, UAY, UAZ, which are just the magnitudes, essentially, of that unit vector in each of these directions. Okay? Okay. And then just solve this. Okay, as before, it's just a determinant. Okay, let's take a look at an example. Okay, so for whatever reason, the author used the MZ to represent this just in general. Find a moment about something Z. Okay, so there are two parts to this. First part, you have to do the cross product of, the vector R from some point along this line. Now you can do, in this case, it's going to be given in terms of the origin, or you can find it in terms of the origin. What you recognize is that as long as you do the cross product, this force, and some point, this R represents some point essentially on this axis. Anywhere along this axis, if you do the cross product of that, it'll give you the same result. Okay, so first thing is, you can find this M of Z, which they're stating essentially is the moment about along this line of action. Which is represented by X. Okay, that's what they're asking for here. Right. The first part is find F in Cartesian form. Then you represent U. You can do this first, however, whatever ordering. But these are the four main steps. Then what you recognize is just the unit vector in the I direction. It's just going to be 1 times I, essentially, right? Or in the X direction, it's just 1I. And then find the position vector. Okay? So we need to be able to do that. So from the information given us, and it looks like the angles are given, so we can use direction cosines to find, break this up into its components. And then we can recognize that, if you see where this handle from the origin straight across here is just going to be 0.3 meters. Okay? So you go through the process here. Looks like we're one more here. Okay. So we've already got that. Unit vector in direction of X is just 1I. ROA. Sorry. The other part of this one, of course, is you have from here to here and from here to here where the force is being applied. We just don't have an X component, so we do have a Y component also. All right, so here's our ROA. And like I said, it doesn't necessarily have to be to to the origin, but it's simpler because it's given in terms of the origin here. Okay, and then the force, just using the direction cosines for that, you can come up with the components. Okay, then you can just do the triple scalar product to come up with M of Z. Okay, and here it is. So you go through and solve this. This, of course, gives us a scalar value. And the end result is just going to be 17.4 Newton meters. And since it's positive, we know it's going to be in the counterclockwise. Okay. So the rotation essentially is, if you think about it, looking straight along this axis, you have a rotation in the counterclockwise fashion around this. Okay. Okay. So here's another one. And in this case, we're going to look at about this axis A-A, as the author called here, right? And as before, what do we need? Well, we're going to do the unit vector UA, okay, and then ROA, and then also F. Find the force vector, and we're given the angles here, so similar to what we had previously. And then we could do the triple scalar product to find M of A. Okay. All right, so the first thing is we can identify an axis, and from the problem you'll notice that Y is parallel to A, so we can just use J for that, or 1J, okay, in the positive Y direction. And then we have ROA, which is essentially, we start from the origin down here, and we recognize that in the A direction there's nothing, which is just J, but it's going back in the negative X direction. So even though it wasn't shown, oh, sorry, it is right here. In the negative X direction, essentially, is it's going back 100 millimeters, which is just 0.1 meters, so it's negative because it's going in the negative X direction. And then in the Z direction, we're going up, okay, 0.15 because it goes up by 0.1 and then 0.5, okay? So there's our ROA. And then we can use the direction cosines. We start with this 30 newtons, and we use direction cosines to find the components of the force. Then we can go, then we go and use the triple scalar product, and we just dot it with UA, and here's the end result when we do that. And the result is 4.37 Newton meters. In this case, it is going to be in the counterclockwise fashion about this. It's hard to see, like, visualize this, right? Okay. And, think about, like, if it's clockwise or counterclockwise, if it's going to come out to be positive, and what did we define as being the positive y? Well, if you go back here, positive y is going to be off to the right, okay? So here's my j. So I'm just saying, like, off to the right is my positive y direction, right? Just essentially found, like, the right-hand rule for that, okay? So this is like positive x, positive y, and positive z, okay? So if we're looking at it from this direction in here, then you would see that it's going to be counterclockwise, okay? All right, moment of a couple. Okay, so what a couple is, well, let's take a look at an example first, or an application first, is that there's certain cases where you're not applying like a net or net translation or a net force in a certain direction, one direction or another. If you want to apply pure rotation, okay, so like in this case, you're turning this wheel, rotating this wheel, applying a certain force in one direction, equal and opposite force in another direction. Well, if you had done like analysis of this and you wanted to sum like all the forces you're being applied in certain direction, like in this case, you would say, like, maybe this is the x direction, that whatever force this going in this direction, you have an equal and opposite one going in the opposite direction, okay? So there's no translation of this object. These two forces are just going to be used just for pure rotation. Okay, so there's often a case like that. We want to look at forces that just cause rotation and no translation. Okay, so this just shows you two different cases here. And the net result of this is that you have essentially the same torque or moment to rotate this wheel. In one case, you have a greater force acting at a shorter distance. In this case, you have a larger force acting at a greater distance. And here's another example where you have a steering wheel, okay? And they call that couple moment, right? Just pure rotation. So pulling down with some force and pushing up with the equal and opposite force in the other direction, right? Here's one, right? You can think about this. Don't have power steering. What does it require? Larger steering wheel or smaller steering wheel, right? Of course, it'd be a larger one. Okay, so how would you come up with that moment couple? All right, you have two forces, they're equal, and they're in opposite directions. All you have to do is just do the distance between them and just do the cross product between the two, okay? And one of the things you're going to notice here, and so you have the correct sign, is that the vector, typically we're going to start from the negative f direction and then go to the positive f1, right? Okay, so if you write it like that, then you keep the signs in mind. Otherwise, if you wrote it the other direction and did this f, so, or, if you had done from here to the negative f, that would have also been fine. And they both would equal each other because, one is just the negative. The r would just be the negative of the other, okay? Just remember that it's going from, like, if you start from, one side and going to the force vector f, okay? All right, so you do that. You could do a scalar. You could use a scalar analysis or a vector analysis, or if you have three-dimensional case. And as I said, before, it's like there's a net force is equal to 0, right? Because if you thought about this plane, you have one made by these two forces. It's like you have one force acting in one direction, which is equal and opposite this force, okay? So this is like just negative F. So if you added these two together, you come up with 0. All right? So one of the things here is you'll note is that the moment only depends upon the distances between those two forces here. Okay? So let's say you applied, this is an object, I don't know, whatever it is, a plate, let's say, and you applied this moment somewhere on this plate. What you'll notice that you could apply this anywhere and you would still get rotation of the plate, right? And just to step back for a minute, to go back to that other wheel problem, let's say, here, right? You know, whether or not you applied the moment by forces acting here, here, or here, it really doesn't matter. It could be anywhere along this, as long as it's in these defined directions. You apply this moment anywhere, it's going to cause rotation of this wheel, okay? So that's one of the key things to go and solve these types of problems with couples. Okay, and then you can add moments together like you could any vector, right? So if you have some moments defined, moment vectors already defined for an object, you can go through and add these like you would and come up with a resultant moment vector. Okay. All right, so here's an example, two-dimensional. Okay, so in this case, what we want to do is we want to find an unknown force, but we essentially going to take this same approach. What we're saying is that, if you add two couples together, you're going to come up with 1.5 kilonewton meters. That's the desired couple, okay? And if we look at this, we have this force acting here, and we have an equal and opposite force acting at some distance at 0.9 meters. And then you have another one here, 2 kilonewtons act in this direction, and then in this direction it's also 2 k newtons. And they equal in opposite direction. We have a distance between those two. So essentially, you're going to find like a couple due to these two, the couple due to these two, and you got to think about it's two-dimensional, so you got to think about clockwise or counterclockwise rotation. And you take those two and you add them together, and that's going to give you this. Okay. Okay, so that's really pretty basic. You can go ahead and solve this one. Okay. Now, another problem, in this case, this one is, it's a three-dimensional problem, essentially. So we need to follow a similar approach. Let's see. So we have a 450 Newton force acting in the assembly. Okay. And we have FA and these two forces, FA and FB, and these two are equal and opposite, and they have some distance essentially between them, or a vector that can represent the distance between them. And we're just going to find M equal to R cross F like before, okay? And since they're equal and opposite, like I said, it's 450 for one, 450 for the other. So we can do from here to FB. So this would be FB, okay? Since we're starting from this point and going over to this one. If we had gone in the other direction, we could have started here and gone in that direction. Then it would have been, RBA, and then FA would have been the force vector, okay? So let's just go through the process, calculate it, and here's our RAB, here's our FB, and then we do the cross product of that to come up with the end result, okay? So this is the couple, right? The couple moment on this particular system or object, okay? Now, if you found this, what it would be that, let's say if you're trying to find the summation of all the moments, this would be the moment due to these two forces, right? In this case, it is the only two involved. These are the only two forces, or only one couple moment involved, okay? All right. Group problem, okay? Okay, so this one, now your same thing, you're looking for the resultant couple, so you have a couple due to these forces here, and a couple due to these forces here, okay? So you have a couple different approaches. You could consider these to be, vectors and handle them that way. Or since they're both in the same XY plane, it's probably easier just to think about them in terms of scalars, okay? So what we'll need to do is we can break these down into X and Y directions or X and Y components of these so we can come up with, essentially you'll have, an X component to this couple, Y component to this couple, and the same thing here, an X and a Y component to this couple here too. Okay, so we have like four parts of it, and then we can add these together to determine the end result. Okay, and here we go. Okay, so first part is, in this case, you have looking at this one first. Here is a component of a couple that would cause rotation. This is vertically up, but this one would cause rotation that let's say I had force this way and one acting down, that would cause counterclockwise rotation. And then this one, of course, you have a force acting off in this direction and then one off in this direction here. Okay, and there's no distance between those two. So now what you'll find is those two just essentially cancel each other out. Okay, and then do the same thing. Okay, so they're talking about this is the only one that causes a couple, right? Because if you looked at the X component, you have an X component force acting in this direction, and in this case, you have an X component of force acting in that direction, right? So those two, there's no distance between them. If you drew the line straight out of those forces, they would cross over each other, and there's no distance between them. So this essentially adds nothing. The X component adds nothing to this couple, right? And we have the same thing for the other one. Okay. This one, define it as being acting up. Well, thinking about the force that's acting up, the component of the force that's acting up, the component of the force that's acting down. And now if you notice that this component is acting right along this line, the Y component and the Y component, this one's acting straight along this line. So the Y component doesn't do anything for this. It's only going to be the X component, which is this part of the force that creates a couple. Okay, and then, so what you'll find is that it's going to be just the this component, okay, the 4/5 times 80, and then that gives you your so it's just this component, of course, and then that's the 64 times 4, and then you got to pay attention to, okay, would it cause counterclockwise about some point in the center, or clockwise about some point in the center here, or cause counterclockwise rotation. Okay. Now, one of the things you would notice that this would cause rotation of the whole object, so you could actually, move this coupled anywhere you want. But for us, if you just wanted to think about it about a center point between these two, at least where they are right now, it might be easier to think about it somewhere between this. What kind of rotation? Or you can think about it in terms of, hey, what kind of rotation would this cause for the whole object, no matter where it is, okay? And same thing like here, so this is going straight up, this is going straight down. This will cause clockwise rotation. Clockwise rotation. And then this one, this one's acting in this direction, this one's acting in this direction. So this one caused counterclockwise rotation, all right? So this is clockwise, so it's going to be negative. This would cause counterclockwise rotation, like this. So you just find those and add them together. Comes out to be 126 pounds counterclockwise rotation, okay, overall. So the end result is this, okay, of those two. All right, now we have another one. Okay, in this case, you have it's a three-dimensional case to handle it. So you notice you have distances in the X and Y, and then you have a vector acting straight up here. One going straight down, one going straight up. Okay. So here's our forces, and the same thing as before. You want to get this distance between the two, so you can go from, here to here if you want, or from here to here. Just recognize that this becomes a negative F. Okay. So going from here to here, we have right along the y-axis. Okay, so this is just going to be the distance from here to here, which is 300 plus 200. Okay, so 500 millimeters or 0.5 meters. And F, of course, is just in the K direction, so straight up. Okay. So we set R to RAB, which is, from here to here. Okay, then you just find the cross product as before, right? So not too much to this problem. RAB, just find the differences. So it's just the length from going from here to here. Okay. Oh, sorry. One part I missed is that this is 200 and this is 300, right? So it's a little bit out on the bar, a little bit further out. Okay. So that gives us that 0.1 difference, okay, because it goes out by +1 in the x direction, right? Okay, and then so we have RAB. F is just 80K, 8K newtons. Okay, so it's in the K direction, just 80 newtons in the K direction, right? And then just do the cross product of that. And your end result is just going to be 40I minus 8J Newton meters. Okay. So not too much. These are just showing you the, determine the couples, and depending upon if it's 3-dimensional or 2-dimensional, right? Key point here is that you have two forces equal and opposite, and they're acting at a distance, some distance between them. You have some distance between those two, okay? And you can also find the moment. Okay, so that's good for now. That's up to 4.6.